Actually, these are not the slides because we have.
Okay, we are going to get started here with tutorial track B, which is on the theme of modeling and measuring human decisions. We are going to have this tutorial divided into parts. There are 4 of us that work together on this tutorial. Myself with Ngoc Nguyen from University of Dayton. And then we have Stephanie Ekman and Frauke Kreuter from University of Maryland. They are right now sitting in the back. They are going to take the second part of this tutorial. So we have divided this in sort of a more cognitive modeling and theoretical approach to modeling human decision-making. And then we are going to go to the human-centered approaches for data collection for machine learning. And then we are going to turn to the practical challenges of survey design and survey research, how to assure data quality. And so together, these 2 perspectives, the theoretical and practical foundations, provide us more information for modeling human decision-making. So let's start with the first part, which will involve Ngoc and myself. So I usually start, when I talk about modeling human decision-making, I start with what is decision-making, and sometimes not all in the audience are aware of what decision-making is or how, what is the essential aspect of decision-making. So I'm going to start with the traditional approach to decision-making. So the essence of decision-making is choice, having the ability to select among alternatives. And so in the classical perspective of choice, we have explicit alternatives provided to us, and there is an assumption that there might be some uncertain event with some probability and then associated outcomes with the various aspects of those probabilities. So the assumption is that we can calculate what is the best action to take by looking into the expected value. What are the probabilities of those events? What are the outcomes that we are going to get? And therefore, we can calculate an expected value for each of the 2 options and presumably select the option that has the highest expected value. So that's classical utility theory, but we are here also to discover that this is not the way humans make choices. The way humans make choices from the very beginning was contested as not being utility-based. So prospect theory, which is up to today one of the most well-known theories of risky decision-making, essentially transforms this utility function and the value function. So essentially proposing that humans don't perceive probabilities in exactly the way they are in nature. Rather, humans overweight low probabilities and underweight higher probabilities. This theory also proposes that the value is different from losses than for gains, in a way that there is some form of diminishing sensitivity where higher values are more similar to each other than lower values, but also losses loom larger than gains. So essentially, they propose a transformation of this expected value with the new functions of probability and value and outcome, okay? And of course, this theory has been validated greatly, very robust in many different experiments, but usually those are experiments that are based on descriptions. So you are provided with explicit options, explicit probabilities, explicit outcomes. So another perspective to this idea is the Heuristics and Biases program, led by Kahneman and Tversky, but also in a different way by Gergi-Gerenzer, where the idea was to make it more ecological. That is, the rules that humans use or the heuristics that humans use in making decisions depend on the environment that humans confront. And the idea is that some of those heuristics that humans use are actually pretty accurate, and they can lead to very good decisions very rapidly. But there are others that can also lead to biases. And so we need to explore more when and how those heuristics really evolve over time. So there is a very long list of heuristics and biases that keeps growing, right? But we need to know more about the source of those heuristics. This is an example of a common bias that is presented in the literature. I'm sure many of you would know this example, but I'm going to go through just to make the point of this. So the classical example is about an Asian disease where you have a number of people that will die, are expected to die from this disease, 600 people. And there are two alternative programs here. Program A, whatever it is, if it is adopted, 200 people will be saved. In Program B, if it is adopted, there is a 1/3 probability that 600 people will be saved, and 2/3 probabilities that no people will be saved. And then, this is the example of prospect theory type of problems. So then people are asked, which program would you choose? So the idea is people choose between one of those two options, Program A or Program B. And then exactly the same problem is framed in a different way. The same problem of 600 people are presented as, if Program A is adopted, 400 people will die. And if Program B is adopted, there will be a 1/3 probability that no one will die, and a 2/3 probability that 600 people will die. And again, people are asked, which of the two programs would you choose? The main effect here is that when the problems are presented in a positive way, people are going to be more risk averse. If things are presented in a negative way, people are going to be more risk seeking. And, this is a well-known effect also that has been replicated many, many times. And it's been used actually practically in many different ways, in marketing, in finance, in health, right? And it comes from the idea that losses loom larger than gains, and this idea that we perceive losses in different ways. But of course, many, many explanations as to why we do that are also needed. And there has been probably, 100,000, I don't know for sure, but many, many studies trying to explain just this very simple effect. Now, let me go to the other extreme of decision-making, and that is naturalistic decision-making. This type of decision approach and study is not very well known in academia. But is actually very common in practical settings, like in the military, Navy, Air Force. They all know the work of Gary Klein. Gary Klein and many others actually were against this very traditional approach of studying decision-making because it was very constrained to very concrete examples and really didn't translate outside of the laboratory. That was their main concerns. And so they went actually out to the real world, and their methods are based on observation, interviews, task analysis, finding critical events, and be able to rely this on observation of expert decision makers in situ. So that we can determine what knowledge they use in making decisions. So one of the anecdotes from this book, which is called The Sources of Power, from Gary Klein, while he was on the truck with firefighters trying to figure out how they make decisions, is that he asked them, so what, stopped them at a critical incident point, and said, so how did you make this decision? And the answer was, I don't make a decision, I just know what to do in this moment. So that was some puzzle for him, and he ultimately developed this idea of a recognition prime decision model. And the recognition prime decision model was actually very influential in my own work because it starts with the idea that, in fact, we look at similarities of situations in the world and what we have experienced in the past. And then in his idea is if the situation is similar, then we can look at the recognition of various aspects, the goals, the cues, the expectancies, and then we can do a mental simulation of potential courses of action. Okay, it went away again. So something is going on here. Okay, so then we go in a mental simulation of potential courses of action, and sort of we think about what if I do A, what if I do B, and then finally select what is going to work. So this is, I believe, very accurate in terms of how people make decisions in the real world. However, this was never formalized. So there were a few attempts to formalize this idea computationally, but none of those, as far as I know, were actually formalized. So now we come to dynamic decision-making, which is the process of assessing and choosing among alternatives in a complex environment while the environment is simultaneously changing. So I see dynamic decision-making as an intermediary between the two extremes that we just discussed. And a main proponent of dynamic decision-making was Brent Bremer. And one idea that he brought and supported was the use of micro-worlds. So he used control theory as a framework to analyze this type of directed behavior, but using games, essentially. He called them micro-worlds that are going to be abstracting characteristics of the real world and represented in some dynamic simulation that then he can use to collect data, not only from experts, but also from novices. Importantly, he highlighted the learning process and decisions from experience rather than relying on very static descriptions of the alternatives. And so he highlighted the idea of feedback, right? So the way we make decisions is we explore, we try out some possibilities, and we observe what the effect of our actions is. So Ward Edwards, long ago, obviously not the only person, many others, but he put it very clearly in this quote that we need dynamic decision theories, not static decision theories. And unfortunately, our field of decision making is largely focused on static decision theory. So this is where instance-based learning, what this tutorial is about, comes from. So the idea is to address all these gaps by creating this theory that would explain how humans form a mental model of the environment, how the human mental model of the environment evolves over time with experience, and how humans use this model to make decisions when interacting with that dynamic environment. And we rely on microworlds. That's either a benefit or a restriction or whatever way you want to see it, but it's definitely not static environments. They are dynamic environments that change over time, and it has been applied to a large number of microworlds and also actual video games. Importantly, this theory was implemented computationally. And it was implemented computationally by relying on cognitive architectures. So cognitive architecture started with Alan Newell, our own Alan Newell at Carnegie Mellon, who proposed a single system, the mind, that would produce all aspects of human behavior. All the representations of the cognitive steps that would be needed to perform a task would be part of this complex cognitive system. He died before he fully realized this idea, but he does have the idea clearly outlined in a series of books. John Anderson, who's here, and Christian Levier, my colleague, developed a cognitive architecture that is called ACTAR. And it's a unified theory of cognition that allows to represent from perception to action, decision-making, learning, several of the cognitive functions that humans perform. It has two levels, a symbolic representation and a sub-symbolic or statistical set of methods to manipulate that symbolic representations. Now, instance-based learning theory came from that idea. That cognitive architecture was actually initially implemented within the ACTAR architecture. And this picture here just illustrates, just like the recognition prime decision model, what the process is. But here we try to actually incorporate the traditional approach of understanding. Norm, we don't have a battery on this one anymore. So we try to incorporate the traditional decision-making processes like judgment and choice with the naturalistic decision-making approaches like recognition and feedback. And so the idea of this process is that people recognize a situation in the environment by retrieving.
Sorry.
I don't know, back.
Yep. Sorry.
By retrieving similar instances from memory. And then evaluate each potential action according to the utility of those similar instances or decisions that were made in the past. And then, like in Gary Klein's model, we mentally explore those various alternatives to evaluate their potential value sequentially, and then execute the choice that has the maximum expected utility up to that point. I'm going to be more precise here in a minute. And then we reevaluate those decisions that we made by using the observed feedback from the environment and updating our instances in memory. So let me go over what is an instance, because that's going to be needed for the next part. So the idea is that each decision that we make is stored in the form of an instance in memory that has the contextual features used for a decision, the action or decision taken, and the outcome. Now here I'm going to use outcome, expected utility, and utility in similar ways. What happens is that we first determine what is the expected utility or expected outcome. I'm using those as synonymous. And then when you receive feedback, you know exactly what the experience utility or actual outcome was. So each potential action then is evaluated according to this similarity. So imagine that you have these instances, T1 and T2 at 2 different times, and now you are in T3, you evaluate the similarity between the situation in the current time with those instances in memory. Now, to determine the action to take, you use that similarity to calculate what is called the expected utility or blended value. Again, I will be precise in a minute. And then you choose the option, the action to take that has the highest expected value. Okay? Whenever you get feedback, that expected value is modified to be the actual outcome received from the environment. So this is the math. You start with calculation of the activation, and this is for every instance in memory. You calculate at each time, you calculate the activation of that instance by using this formula. This formula represents the frequency effects, the recency effects, the similarity effects, and the noise. So in each time, for each instance, this calculation is done, which represents how we retrieve information, how humans retrieve information from memory based on those aspects: frequency, recency, similarity, and noise. Then we use that activation value to calculate the probability of retrieving that instance from memory. And then that probability is used to calculate the expected utility or blended value of each option. Option A, option B, which can have many instances in them, are blended together to calculate the expected value of each of them, of each of the options. So following on the idea of what does this have to do with artificial intelligence, well, Herb Simon put it also very accurately, and Herb Simon was also here at Carnegie Mellon. So AI can first be directed toward getting computers to do smart things. That is not what IBL does. IBL is not going to be, it's not an optimizing algorithm, right? It's a human-like algorithm, and it is a cognitive algorithm. But one way of doing AI is to use machine to do those powerful optimizations, right, that we need. But also he said that AI, he called it sometimes called cognitive simulation or information processing psychology, is also directed at using computers to simulate human beings and to help them be better at the decisions they make. So to put it more generally, IBL is one example of many others that are cognitive AI algorithms. These are the cognitive plausible algorithms that can emulate human decision-making. They rely on cognitive theory. They are dynamic and actionable agents, so obviously they are implemented computationally. They can represent individuals as well as populations, and they can be autonomously making decisions based on the theory. We are trying to use these type of models to support the human-AI complementarity in various ways by doing training interventions, by guiding the recommendations that the machine AI provide to the humans, by collaborating with humans, by generating also data sets that can be used by machine learning. So I'm going to let Ngoc now get you more into a particular implementation of this theory.
Okay, so we've just gone over the basics of instance-based learning theory. So let's look at how we can actually apply it in practice. So one case study we're gonna look at today is in two-dimensional navigation. So this is an example of sequential decision-making task where the agent, so I'm gonna use the word agents here, which is gonna be an AI agents or they're gonna be human agents. So the agent need to take action step by steps. And these steps are interdependent. That means each move, each action depends on the earlier choices. So the agents must think over about how about the past choices gonna influence the future outcome to reach the goal. So this section is supposed to be very hands-on, so it could be great. You can follow or you see a demonstration. Okay, so before getting to that, let's take a step back and try this very interactive, simple game. So this is the link. So this is we call this the Treasure Hunter Challenge. Okay, so in this game, you're supposed to navigate the environment, which is the grid here, and you find a hidden treasure. Okay. And the goal in each episode, you need to reach the highest value treasures. Okay, so here's some information about the game before we start. You can use the arrow keys to move, to take action. Each episode has a limited number of steps, and you need to figure it out how many. And we have 5 episodes in total. So after finishing that, you can download the log file to review your results. Okay, so let's click on this link, and we're gonna leave you about 2 to 3 minutes just to try this game. So if you click on this link, okay, it should be like this one.
Can you tell them they all have?
Oh yes. So if you click on the presentation slides that we share in the Google Drive, you can see the link and you can click it directly. Okay. So we share the slide in PDF, and when you click on the links on the PDF, you can direct you to the game. Okay, so if you figure it out, that's what is the highest value treasures? Sorry? 50? Yes, great one. Did you notice how many treasures in the environment? 2, yes, it's correct. So anything else that you notice in the environment that influences your choice? Anything else? Yes, there's a cliff, or this is the endpoint somewhere here. Yeah, it's great players in general. Yep, great. So now the goal is that, so the goal here, this is type, or we call that sequential decision making, feedback delay, where you see that you take a sequence of steps and the true outcomes only revealed at the end of the sequence. And so this is very common in a dynamic decision-making task. And you can see that have different applications, and the navigation task is one of examples. So instead of us, humans, playing the game, so now we're going to build an agent that's going to play exactly the same game as navigation task. And we want, as Coty mentioned, that we want to build agents that human-like behavior, so that the agents, we're going to use an instance-based learning model to make a decision. Okay, so that's the goal today. Okay, so the objective of this section, there are 2 objectives. First, I'm going to introduce you to Speedy IBL library. This is the Python open source computational Python library, where it can have you researchers or AI practitioners to quickly develop the human-like decision-making models based on instance-based learning theory. And then the second one, we're gonna apply it concretely in this game in two-dimensional navigation task. Okay, And there are actually quite several Python libraries for instance-based learning theory, and the speedy IBL is one of them. I see that its main advantages is simplicity. So where you can, which makes it easier to adapt, extend, and actually to customize the models to apply in different applications. Okay. So first of all, I'm going to introduce you to some core functions, parameters of the library where you can implement the IBL model, IBL agent, and then we're going to apply it in the task that we have just described, and to see that how the behavior is. Okay. So if you click on, I'm going to share also the link on the GitHub. So like we shared that we're supposed to, this is very hands-on, so it could be great. You can following along when I do a demonstration for this task. Okay. So before getting to the coding and see that how the agent's gonna implement it for this task, here is some concrete applications that we have been used speedy IBL for the simulated control operations. As you can see here that we can apply it in a single agent tasks. For example, the search and rescue for the games like Pac-Man, and we also apply it to multi-agent tasks where the cooperation is needed. For example, here on the first one is a cooperative navigation where multiple agents need to cooperate to find all the targets. Or we have in the object transportation where the coordination is very important, or we call the task is moving target, where the actions must be, of all the agents must be exactly the same. Okay, we call that fully cooperative. So in general, you can use speedy IBL library to apply to the sequential decision-making task in your applications as long as it can be formalized as sequential decision-making. Okay, so how can install a speedy IBL? It's Python library, so it's very similar like any Python library that you use. How many of you have experience with Python? Okay, great, so I think most of you. So just pip install the name of library. So the name of library here is speedy IBL. So we have two ways to follow this hands-on section here. You can run the online Jupyter Notebook, which I use Google Colab, just quick, easy, no installation needed. Or you can just download the code in GitHub and you run it locally. I would recommend to use a virtual environment, so you can use the built-in virtual environment from Python, or you can use like Conda, mini Conda to install this. So two ways. So either way is fine. So I will show you in just a moment with this one. Okay, so core architecture. So the core architecture of all the speedy IBL library is in the class agent. So first of all, we need to import the class agent. So this is the architecture that Coty presented for instance-based learning theory. So the process of recognition, judgment, choice, and evaluations, and also update the outcomes into the memory is implemented through a couple of essential functions and also parameters. So I'm going to start first with the parameter for this library, for the agent. Okay, so there are different parameters, but there are three key essential parameters that usually we need to control the behavior, control how the agent learn and make decisions. So the first one is the utility for unknown options. For example, when you don't know about the options of what is going to be utility. So the high value of default utility encourages the exploration rather than satisfaction. If you set the default utility is low, you're more satisfied. The agent is more satisfied. Okay, you can think of that. The noise also represents the agent's exploration ability. The decay, also captured in instance-based learning theory, show that how quickly the memory fade here. So the value of decay, so the low value of decay represents the long-lasting memory. High value, this means you forget something very quickly, the agent. Okay. Other optional parameter you can indicate is the penalty for the mismatch similarity between the instances, or also the how large of the memory can to store this one. Okay, so more detail we can use the utility function, the helper function here to see all that description is parameters. But in general, the first three parameters is going to define the control, how the agent going to learn and also behave. Okay, so that is the kind of characteristics. So now how the agent's going to interact with the environment is captured through the method of the agents. So we also have some essential primary methods. The first one is to choose the action. The agent needs to choose the action here from the list of options. And then they need to get the store that feedback from the environment into the memory. And also, if it is a sequential decision-making task where feedback is delayed, then we need to update. Okay, so these are the three things that we may need to use here. Also, there are a couple of utility or the functions that's going to help for analysis behavior of the agent. I will get into more concrete when you see when we apply in that example. But let me briefly walk you through this. For example, you might want to know what is in the memory of the agent. So then the function instances is help. It's going to list all the instances stored in an agent memory. And then we can also add this experience into the memory, the agent. Computational activation, compute probability, and also blended values are all the three functions can help you trace how activation is calculated, how the retrieval probability, and also how the blended value are calculated. So they are linked to the equations of instance-based learning theory that Coty introduced earlier. Okay, so we find that all these functions help to understand, to trace the behavior of the agents, which is help you to understand a more explainable agent here. Okay, so there's still quite a few functions, and if you want to see more, you can use this helper functions and also this one. Okay, so now I get into before we get into the apply speed IBL for this task, let's take a look at the code of how to run it. Okay. So if you click on this link, again, so this link should be shared with you in the PDF file. Okay, it's gonna point you to the GitHub. It's going to point you to the GitHub of this one, and you can just click on with Open in Collab. So I'm going to click in Open in Collab here. Okay. So as long as you have the Google account, then you can use the Google Collab here. One thing that we need to do, because to run this code, you need the file of the environment, which already built in and provided. So you need to click on this one, okay, files, and upload it to file in the repository, which is util file and grid world. Okay, so grid world is the environment or explain it. Okay, as long as you uploaded the two additional files into the same folder, this one, It's good to go. Okay, so let's start it. Okay, so here. So to install Speedy IBL, you just call pip install Speedy IBL. Here, I'm gonna run it anyway. Okay, so this is how we install the library, which is called here. And like I explained, I'm gonna zoom it a little bit. Okay, so like I explained, everything of the Speedy IBL is agent class. We want to build an agent. So we just form Speedy IBL, we import the class agent, we just run it. And we see that the agents, this is the help agent init. So this is all the parameters that's gonna control the agent's behavior, and so how agent learn, make decisions. Okay, you have here default utility, we said this is default value, we can change it later on. For example, this is how we define the agent. Okay. So that is just how to install the Speedy IBL, import the agent. So let's take a look at how we're gonna apply it, make the agent take action in the two-dimensional task that we just played earlier. Okay, I'm gonna go back here. Okay. So this is just the illustrations of what we're gonna build. We have the environment, which is the real world, like the game that's provided to you for you to play. So now instead of us playing the game, we want the agents gonna play the game. And the agents that we want, the agents have the human-like behavior playing the game. Similar is human. Okay, the process is that gonna be, we need to have the agent is gonna take action. So as you can see in the game, we have 4 actions, up, down, left, right. The agents can take up, down, left, right. And after take action, you also observe something from environment, send you back, right? For example, the cost, -1, or the position of the agent changes. So that is observation reward. Okay, I think that's gonna be, this is very common about sequential in learning from experience. So the agents have no idea about what the environment is, where the treasure, where the goal are. They need to figure it out. They need to figure out by taking action. So that's what we call that learning from experience. Okay. So two things, 2 components that you can see in this one. The first one, the environment. So the environment usually provided to you, and here in this example is a hidden 2D navigation where the agents learn through interaction, exploration of the environment. So this is the hidden environment behind, and you also figured out that, okay, the highest treasure goal is +50, okay, and the low value treasure is +5, and then also the cliff where it is the terminate the game, which is -5. So that's hidden from the agent. And so that's why I'm saying that the environment is imported from the file grid world where we just uploaded here. Okay. So the second component, which is the main component we care about, is the agent, IBL agent. Okay, so the next step is we're gonna define the IBL agent and using the parameters to guide the learning, guide how it make a decision. Okay, we use from Speedy IBL library, we import the agent. And here, like I said, we're gonna set the parameters, the essential parameters. Here, for example, I'm gonna set the default utility is 15. I use the noise 0.25 and decay is default, which is 0.5, right, to set the behavior. So for example, usually we're gonna set with the default values for those parameters, and based on your task, based on your need of your application, we might want to change these parameters to match into your applications. So that's what we do in practice. Okay. So in instance-based learning theory, as Coty introduced you, the main things is this instance, which is the memory unit, a memory chunk is going to store in the agent's memory. And so, for example, it's going to be the tuple of the situation, we call as the context features. So the situation include context features. Also action. What the agent take action in this situation and what's going to be the outcome. And that is, we call that the instance unit, what is called instance, which is the memory unit. So here in this task, which is the navigation task here, the instance, we're going to define exactly the same, which is situation, which is the state, showing what is the position of the agent. And then the action, what the action that the agent take, and then what is the outcome, what they observe from the environment. Okay. And the option choice is we denote this, which is state, and which is situation and action, telling you that in the situation S, what is going to be the action taken in that situation. We call that the choice option. Okay, so let's take the look at how the instances is accumulated in the instance in the agent's memory. Okay, so from the beginning, starting here, the agent has no idea about the environment, what is going to be utility for each action. So it set all the value, which is default utility, if you remember here. I said default utility here is 15. Okay, so now in the memory of the agent, it's gonna set, okay, the outcome, expected outcome for every action in this situation should be 15. And it is timestamp 0, it's from beginning, haven't taken action. Haven't taken any action. I'm gonna set this expectation for every choices, the same, by the value of default utility. Okay, so now at time step 1, that means it's gonna take action to the environment. So for example, the agent, I'm gonna take the action up. Okay, so now it's moving up, and it's observed from the environment that, okay, you get the 1 cost minus 1. So then it's store that new experience into the memory. So now it is from the situation, I take the action up and I observe minus 1 at timestamp 1. Okay. Now in the next timestamp t plus 1, which is timestamp 2. Okay, I take another action up again. And now it is in this situation, which is from this point and moving up, and you observe minus 1. And so we just keep going on like that. And we have all the instances accumulated in the agent's memory over time. Yeah. So that is the structure of how the instance is accumulated, stored in agent memory. Okay, so now at the time step t plus 1. Okay. Let's say at time step t plus 1, you accumulated some instances in the memory, and you're gonna ask which action I'm gonna take, should take at the state, this one, at one state. Okay? So then this is how the instance-based learning theory, they're gonna get all the instances relevant to that situation. For example, here, I'm gonna retrieve from the memory. Okay, in the past, I already take this action. I'm gonna already have this action in the state. okay? And then we calculate what we call is the activation for each instant. We denoted instance 1, instance 2. So we have activation for each instant. And then we have the retrieval probability for each instance based on the activation function, so based on instance-based learning theory. So once we have retrieval probability and then the outcome, like Coty said, we're going to calculate what we call is here is the blended value. So we have many instances, so now we blend it together to decide that what's going to be the blended value for each option. So the option here is the action taking up in the state in this situation, 3, 0. Okay, because here the choice option is the situation and the action. The situation is I'm here, I take action up. And you do the same for the other choice option. For example, that is in this state, I'm gonna take action right. In this state, I'm gonna take action left and down. So I'm gonna compare, then the agent's gonna compare every choice option, the blended values for all the choice options, and take the one with the highest blended value and make the decision. Okay. So that is how the agents make decisions in this grid world, which is two-dimensional grid world. Okay, so here is briefly walking through. Do you see that the helper functions to see that what is in the agent? So this is just a snapshot of the instances stored in the agent memory. Okay, here you see that option. So like explained, there's two things. The first part is the situation. So because it's the matrix, so we just hash it to have the integer. So this is just technical part. Okay, so we hash it into a unique integer. Sorry. And then 3 is just we have 4 options denoted by 0, 1, 2, 3, represent up, down, left, right. And then we have outcome. So we have situation, action, outcome, which is an instant. Okay, one thing you can observe here, which is occurrences. So occurrences actually is the timestamp that the agents take action. Okay, and from the implementation point of view, you can see that the occurrences here is used to implement activation. For example, if this action taken a lot, you can see that the occurrence is going to be the long list of occurrences, which is captured by the frequency. So the more of instances happen in the memory, you can see that the occurrence is going to be a list of the timestamps that is appended into this list, which is we're going to capture through the frequency. The value here is showing the recency of the action. So the occurrences are actually going to capture through this one, as Coty explained it earlier. The sum here is just the sum of the list, right? So the long, which is the frequency, and here, which is the recency, t and plus t prime, the recency here. Okay, so this is what we have in instant, and based on, then we calculate the activation for each instant here. Of course, we not calculated, the library already did that for us, and we just call agents compute activation. And we already know that the time step t, so now we want the time step t plus 1 in the future, what's going to take. And this is just the state converted to the integer, and this is action. So you see that this is return. This one is for activation for the instance 1, instance 3, instance 2, etc. Okay. So then we convert based on this activation. We want to see something more interpretable, or which is like the retrieval probability. So you translate it into a probability, and here you can see that okay. So this one with their action, so the probability is 1 because it just happened 1. And then we convert into the probability. So the probability for activate the instance with the value outcome is -1 is 0.9, or the rest is 0.2. Okay, we do the same. So the last one is based on the activation, based on probability, retrieval probability, we calculate the blended value. So now the blended value is for the choice option, not the instance. Okay, so we just have 4 choice options here. We have for the state and option up, down, left, right. So you see that 1, 2, 3, 4, which is the blended value for the 4 options, up, down, left, right, in the situation S. Okay, so that is how calculated. So we see that usually the agent, based on this, the agent is going to pick the choice option have the highest blended value. Okay, so that is how implemented with the agent. So how the agent make the choice, make decisions. So we use the function choose, agent choose options, very straightforward, how many options you have. So remember the option here, not just action, up, down, left, right, but you have to accompany with the state, because it only makes sense that the option they take in which state, in which situation. So remember again, the option should be the state action. So the agent choose which option, and then because it is the tuple, so we want to know the action in the second one, 0, 1 here, which is the choice, the agent. But the idea is just you use the function agent.choose and then the option to take the action. We'll see that in action in the code just a moment. I'm just walk you through so you see the full picture of what we're going to do. Okay, if you have any questions, feel free to ask, to chime in. Okay, so now the process again, we have the environment, we have the agent take action, what we agent's gonna get back, new observation. Okay, what is gonna change in environment, and also any rewards provided here. Okay, so this step of, we're gonna say that the environment, that step is already coded in the environment, so you don't need to care about that. So the environment taken the action of the agent is gonna return the new state, which is, for example, the new position of the agent. The reward for each step, which, for example, the moving cost is -1. It is the terminal, or this is the end of the game or not, and also the new position of the agent. So that is just showing the new observation of the environment changing after the agent take action. Okay. So like us, when we play, after we play, we observe changes, we record it into the memory. So to record that, to save that, to store that experience, just the instance, a state action outcome into memory, the agent's gonna call the function respond. Okay, so here the agent's gonna save the outcome of the action that they take, the consequence of what they take into the memory. Of course, it's gonna help them to make the better decisions next time. Okay, so that's the idea. The agent take action, agent.choose, and then observe, and then record that experience through agent.respond. Okay. So this step that's just one step. Action, like for example, move up, I observe, I record it, just one step. Just moving one step. So now you keep continuing because it's a sequential of steps, a sequential decision making. So you need to keep looping a number of steps. okay, if it's allowed. And so that's the agent continue doing take action, respond, choose, respond, save this action into the memory, okay? As you can see that they take multiple steps, and at some point they get into a terminal state. For example, they is lucky enough to get into the highest value target, which is 50. Okay. So if you can see that if we just record step 1 minus 1, step 2 minus 1, step 3 minus 1, and then step 4, for example, plus 50. We don't see the connection of all the steps. We miss the consequences. Okay, it's just independently recorded in the instance memory. How do they know that this outcome is achieved because of contributed by all of these previous steps? Right? So if you just record this one, this step, they just recorded independently. We don't see the connection, causal of what lead to this one. Okay, so that is here in the sequential decision-making task, you need to do what we call the credit assignment. When feedback is delayed, that means the true outcome, the big outcome here, is contributed by the previous choices, the past choices. Okay? And that's what we call as a credit assignment. There are different ways for credit assignments. I think there's going on the research in this area about credit assignment. But here in SpeedyIBL, we just implement as the most basic one. We call it equal delay feedback credit assignment. That means, for example, here, once you get into this final true outcome, this is going to be applied to the previous steps. Okay, for example, this is accumulated, it is the return. So 50 and you minus for the step cost, you have 47. And it's going to be assigned retroactively to the previous step. Okay, and so here it's just update and all the past sources have the same value. So from that on, you do the backward. So when looking back, so then you see, okay, this one is contributed is because of the previous steps. That's what we call credit assignment. Okay, so that is the idea of the sequential decision making. So to do that, we need first, we collect all the steps that the agent takes. For example, you recall all the past choices, the history, and then you just call the function equal delay feedback, for we call this total return. The total return is the value, and then you also add it with the cost along the way. And for the episode history, which is all the previous steps. Yes, please. Mm-hmm.
One sec, hold the microphone.
Okay.
I just had a quick question regarding credit assignment and how it is different from the points that each step was gaining as it was being executed.
The discounted, you mean?
Yeah. For example, okay, I might have missed something, but step 1, step 2, step 3 are just...
Can you speak out loud, actually?
Oh, sorry. Each step is a movement in the grid, let's say, right? Mm-hmm. And if at each movement, it gets the cost of making that movement, right? The -1. Mm-hmm. How is the credit assignment different from that? Also better? How is it?
Oh, okay. So you mean like a -1? How credit assignment better for us? So let's see that if I reframe your questions correctly. So you mean like how do I see that the credit assignment helpful for its learning? Okay. So credit assignment is just like when you're looking back, you're connecting the dot. I'm gonna say that's analogy. When you just take action, you don't see the outcome. And you just record it. But you need something like connecting everything together. So when you, at some point, you see you have the true outcome, and then, okay, in retrospect, you look at in the past, and you assign, okay, this is one contribute to where I found it. So yeah, I'm gonna say, this is answer your question, does it? Okay, thanks. Yeah, feel free to ask question and feel free to interrupt. And yeah, this is a great questions, and there are many different techniques. For sure, different techniques to assign back. This is very most basic one. And of course, depending how you assign also influence how the agent, the performance of the agent. Okay, so now let's do the demonstration for the whole process of what we've just gone through. And I also showing you like how the agents, you will see that how the agents make decisions. I will show you how the blended value changes from the first episode to the 100 episodes. Okay, so let me explain what is the episode. Okay, so you take a multiple steps, we call a sequence of actions, and then at some point the game is over. For example, you fall into the agent fall into a cliff, game over. You get into the target, game over. So that is we call one episode. Okay, just a sequence of steps and get into the termination. We call episode. And as we play, the more episodes we play, then it gets better, right? We want to see the learning curve of the agents over time. So we're gonna repeat the agent, let the agent play 100 episodes. And we're gonna see that how it's gonna learn, how it's gonna change through the blended value. Where does involve time? Okay, I'm gonna go back to this one. Okay, this is just to import the environment. Okay, so this is the environment that the agent see here. If you want to see the agent, what you want to see the hidden. I don't know, is this true? Right? Oh no, I don't know. Oh, so this is full. Sorry, this is the parameter that I put. Okay, so if you want to see the full environment, which is hidden from the agent, so this is the true environment behind that the agent needs to learn to figure it out. Here, okay, which is the position. This is the highest value. When you play the game, I guess you figure it out. Okay, so the agent, we already import the agent. Okay. So this is the step that I explained. I have the agent here. I just set default utility. If you don't set anything about the noise and decay, it's gonna be the default value. For example, I think it's gonna be noise or for 0.25, and decay is by default is 0.5. Okay, you can indicate any value, but I'm gonna stick with the default value first, and then we can change this later on. Okay, so now this is how the agents make the choice. Okay, agent choose option. Okay, the option hasn't defined yet. Okay, the option is here. Okay, so we have 4 options in the environment, so this should be like 0, up, down, left, right. Okay, they're associated with the value. Okay, so for example, here we see that it's just like one step. And this one is, again, is encoded for the state. Okay, for the state, this is the matrix, and we convert it to the integers just for the technical implementation. And you take action 1, for example, I just say up, down, left, right. Let's say 1, this is down, for example, at this state. Okay. So now after you take the actions, the agents want to see, okay, what it changes here. They need to call environment step action, which is the action that it selected, which is 1. And then you're gonna observe. Okay, for example, actually 1 is left. You can see here, the agents move from the position here to this position. Okay, so this is a matrix, which 240 encoded the position of the agent or move in this one. So this observe, the agent receive back, okay, your observation, your position is changing in environment. This is the cost, step cost -1. The termination false, keep continue, it's not the termination. And 1, 3, just a location, actually here of the agent. So this is what they getting back. So after having this, it's gonna store in a memory for the agent. So here I have the memory of the agent before. You just call, if you want to inspect the agent's memory, you call agents instances. Okay, nothing, because haven't stored anything. So now you need to store it. The agent, not you, sorry. The agent needs to store the experience that they have from the environment. So it's stored here, and you run the agent instances again. Right? So you see that exactly what we have here. Option, again, I'm going to say this is option should be state together with action. From the beginning, this state, option left, as timestamp 0, which is you don't have any expectation, you just set 15, which is default utility. But now you take that action, real action, actual take action, and you observe it's -1. And it's recorded into the into the agent memory. So keep going with the sequential of decision, and this instance is accumulated in the instance memory. Okay, so now I'm gonna repeat that into a number of steps. Okay, a number of steps. So just putting everything into the for loop and looping to run. For example, the maximum of step is defined, is regulated, is in environment, which is 20 in this game. Okay, so if you click here, you can see that it's 20. So it's environment. Okay, the rule of the game is just 20 steps. And I call this is the function run episode. So now you run 20 steps. Okay, and here is the, so for example, let's say here is true. So then you see the full picture of what is running. Okay. Okay, so this is just one episode. Okay, this is just one episode. The agent start here, it's moving around and around, and then at some point is landed into the cliff and the terminal. This is terminal state, a termination. So that is the sequence of steps. The agent took 16 steps, and then the 16 step is landed into the cliff. So this is the illustration. So if you want to see the full in the code, you see the full environment, you're just testing it. Okay. Okay, so that is a sequential one episode, only one episode. Okay, of course you can see the path moving around, get into a design state, but the agent is supposed to learn to improve it over time, right? So this is just what I illustrate for. This is how they calculate the activation, so you can run that to explore yourself. So again, this is the retrieval probability for two instances. The instances here associate with the outcome 15, they associate with the outcome -20. Okay, and then you need to compute the blended value. The blended value should be only 4 values because we have 4 options. Of course, it's associated with the state S here, up, down, left, right, and you have the blended value. Okay. So now putting it together, they play one episode. I want the agent run 100 episodes, and it's expected to be improved. Okay? The more they learn, it should learn. They improve over time. Okay? So now I'm gonna run it. So another for loop. Okay? So for loop here is episodes. I'm going to play 100 episodes. Okay, in each episode, I'm just call the run IPL episode, just one episode, and just I'm looping it 100 times. Okay. So after that, it's just showing you how the. So let's look at how the blended value, how the agents are gonna make decisions over time. So this is a heat map illustrate. I need to zoom it a little bit out so then so you see the full picture. Okay. So let me explain what is this. So this is environment, and each big cell here, each square is the state. Okay, the state, and in each state I'm gonna divide it by 4, which is for action. So the small triangle here is this option, the choice option, state action. Okay, so in this state, moving up, moving down, moving left, moving right. And from beginning, everything is set to the default utility, which is 15, because the agent hasn't experienced anything before. Okay, so now it takes, let's say, episode 1. Okay, already 2. Okay, anyway. So now when it's in episode 2 or 1, because I slide it a little bit, so you see that this is the blended value. Okay, it's blended value. So the blended value for moving down is minus 0.16. Moving left, plus 11. Moving up 3, moving right 11, moving up 3, moving left about 4. So it's changing. Okay, it's changing. You can also see that they learn something that continue to move right should be penalized. Okay, maybe learn from episode 1. Okay, fast forward, just keep scrolling. And you see that it's gonna update it, the blended value. So the reddish is penalized and negative. The greenish is the higher value. So I'm gonna scroll it. Okay, and just do the end, which is the last episode, episode 100. So now you see the greenish, the darkest green is the path that the agent gonna take. Okay, so for example, the first state, it learned that the best one is moving up. The blended value is plus 37. Continue moving this state, the best one is moving up. Continue here. So they should not go straight because it's the low level value treasure. So the best blended value is just moving right. Okay? And continue moving right, up, right. And this is the path that the agent learn moving down, should moving down, and get to the point. So the greenish, you see that the darkest green is actually the decisions that the agent takes in the last episode, after 100 episodes. So you see that how their blended value, how decision of the agent evolve over time. So now just one agent, okay, one agent playing one episode. Of course, you run this again, the blended value is going to change because another agent is going to learn. Yes, okay. Yes. So that is just one, only one agent playing. So we want to plot something more reliable results. You repeat it, right? We need to, it's just one agent, maybe just one agent learning. How about the other IBO agents? So for reliable results, we just replicate it for 100 simulated agents. Okay, and each agent is going to play 100 episodes. And we want to see the learning curve over time. Okay, so learning curve over time here. So we see that, okay, this is the variance of 100 simulated agents playing 100, actually just 15 episodes here when I plot. So you did see that the improvement of reward, they get higher reward over time. The more the agent play, the better. Okay, and you see that the proportion, the frequency of getting into the suboptimal target kind of decline, decrease supposed to be, and it should be, and the frequency, the proportion of getting into the highest value be increasing. Okay. So you will see that, okay, but sometimes this kind of high, okay, how is gonna improve learning? How can we improve learning? So you remember that the parameters that control how agent learn, how agent make decisions, okay? So one of the things is, of course, one reward that you're gonna shape the agent learn, but one of the things you can explore is how the parameters that's going to control the agent learn and also make decisions. Okay, so this is the interactive way where you help you to play with different parameters of the agent. So if you click on this link, okay, this is going to point you into, so if you're curious what is going to be changes with the different parameter configuration of the agents, you can click on this link. So for example, here is the agent with default utility 15, decay 0.5, noise 0.25. This is another agent, default utility 5, the rest are noise decay the same. So usually we fix one to see the effect. So let's see how different configured agents play differently. So I'm just let the agent play 50 episodes, and to have the reliable results, I'm gonna repeat it 100 times. And we click and to see how the learning curve of comparison is gonna change. Okay. So actually you can click and you see how it's figured. You see how it's changing with different parameter configuration. Okay. So for example, here you see that default utility 15, the agents learn much better. Why? Can anyone have an idea? So for example, if you remember the default utility, when you set the default utility here is just 5, which is the orange one. The agent is more satisfying. Okay, so then the proportion of get into the suboptimal reward, which is the easy low value, is high because it's just, okay, 5 is okay. It's kind of the same as the low value. So I'm just keep going to that way. I just don't want to explore the other way. That is good enough for me to explore. But if you set it high, so that means 5 is not enough, let's keep exploring. So that's one of the parameters you're gonna play. So yeah, I think that you're gonna play with different value of decay parameters here to see that, okay, how agents behave differently in this way. And so that's it for this section. So I'm sticking around. If you have any questions, feel free to ask. Okay.
We are going to be around. If you have more questions, we can take only one question before we go to the second phase, if anyone has a question.
Hello, thanks for the tutorial. Yes, I tried setting the initial utility value to 50 and the final reward is even worse than 5. Is it like some exploration-exploitation trade-off?
The default utility?
Yes, I tried setting to 50, and the final reward is super low.
50.
50, yes,
Okay,
50.
50. And you wondering why it's super low.
Yes, it's even worse than 5.
Okay. So 50, so maybe because the high value is going to be exploration, maybe just roaming around to get into the expectation. So it's going to be, for example, 100 or 50 run might not enough for the agents to learn. Good enough, right? So they want to more episodes. So you might want to increase, let's say, let the agents run more and to see if it's any like improvement. It's gonna slow, right? It's gonna slow because it's just roaming around to explore the environment because the value is super high. It's not get into the goal that satisfy that my expectation. Okay. So this might get to explore everything before it's settled down to what is gonna be the best decision in this case. Okay. Yeah. So that is the great play with that. Yeah.
Thanks.
Yeah. Okay. Thank you for the tutorial. So my question is, what if the goal is not objective? It's not clear. Like here, it was maximize the value, like the outcome. What if the outcome is subjective and not objective?
The outcome is
like not numeric.
So you mean that the decisions is not optimized, right? Is this your question?
Yes, like maximize quality instead of quantity. What if the objective is quality?
Okay, so I think this is a great question. It's gonna link to, for example, if you happen to know about reinforcement learning. So this is also reinforcement learned from experience. And what's driven for the reinforcement learning is optimize, it's going to maximize, it's formulate the problem as a maximize accumulated reward. But what is the agent is going to learn is you remember the two goals, is to mimic what human gonna make decisions. So all the mechanism behind of these agents is based on the experience, it's the memory that is restored. Okay.
So every decision in IBL has this aspect of utility, but we take the utility concept very loosely. You know, whether it is higher quality, lower quality, or a high point or low point, ultimately in the implementation of the theory needs to be converted to a number. So let's say quality from 0 to 100. If that's your measure of utility, you just use 0 to 100 as your metric, right? So for implementation purposes, you turn those qualitative aspects into numbers. Okay.